Hello everyone, this is Oshani from Cheenta.com. So I was working on number theory in our Math Olympiad class at Cheenta.com, and something very interesting came up. There is a connection between number theory and geometry, two of my favorite subjects, and I wanted to share this connection with the entire community. So that's why we are making this video. So we were studying something called the reduced residue class. Reduced residue class, which I will explain in a moment. And I was also working on symmetry. So I will explain that in a moment. And somehow there is a beautiful connection between these two parts of seemingly unrelated topics. So what is the reduced residue class? Well, let's take the number 8 and let us write down all the numbers which are less than 8 and which has HCF 1 with 8. That means the number and 8 has the highest common factor, or GCD, as 1. So what are those numbers? Well, 1, 3, 5 and 7, right? Each of these numbers are smaller than 8 and they are having HCF 1 or GCD 1 with 8. So this particular set is known as the reduced residue class of 8. So in the comment section, can you tell me what is the reduced residue class of 20? All the numbers which are less than 20 and co-prime to 20, that is their HCF with 20 is 1. Can you tell me what are those numbers? Okay, so this is what the reduced residue class is, and in number theory we study these reduced residue classes and Euler's Totient function. There is a whole area of this discussion. But secretly, this is actually a group. So maybe you've heard about group theory. It's a very beautiful part of mathematics. In fact, it was also part of my PhD thesis. I studied something called geometric group theory. Maybe one day I'll tell you more about that. So secretly, this set is a group. And this particular group is very important because it also represents symmetries. So I will not explain what is a group today, but I will explain what is symmetry. So let's take an equilateral triangle, A, B, C. A symmetry of the equilateral triangle is a motion. That means you move the points A, B and C, is a motion such that before and after the motion you will have the same picture. It's a very crude way of saying it, but that's exactly what's happening. Before and after the motion you have the same picture. So I'll give you an example of a symmetry. Why don't you take the reflection about the median? So think of this median as the mirror and you reflect the equilateral triangle about this median. What you get is this point will go here, this point will go here, this line will go here, this line will go here, but the output picture will be the same as the input picture. The output picture will be the same as the input picture. So this is the symmetry. This is a reflexive symmetry This reflection is an example of a symmetry of this equilateral triangle. What we would like to do is to think about this set as a set of symmetries. Set of symmetries of certain geometric figure. And what figure is that? Well, the number 8 is the clue. It's the octagon. So let's draw the octagon. So to draw the octagon, there is a simple way. You just draw two perpendicular lines. So these are reference lines. Now in each quadrant, you will need two sides or two edges of the octagon. So, and it has to be perfectly symmetric. So it's kind of like this. And you can practice drawing this actually. If you carefully draw stuff, you will learn a lot about them. But you have to do this carefully. So you have to carefully draw it. Okay, so here we go. We have the octagon. Now I'm going to draw the point O and A, B, C, D, E, F, G, H. Okay, so what is an example of a symmetry of the octagon? Well, one example is you rotate by 45 degrees. You rotate the octagon by 45 degrees about the center O. Rotate by 45 degrees about center O. So the point A will go to the point B, B will go to C, C will go to D, D will go to E, E will go to F, F will go to G, G will go to H, and H will come back to A. So the entire octagon will turn by 45 degrees and you will get the same picture back. That is an example of a symmetry. So I'll write it as rotation by 45 degrees. That entire thing is a symmetry of the octagon. Okay, so there are other symmetries of the octagon which are quite useful. So another symmetry that, let's talk about another symmetry. This one is rotation by 135 degrees. That is 3 times 45. Rotation by 135 degrees. There is another symmetry which is a rotation by 5 times 45 degrees. 5 times 45 degrees. That is 225 degrees. 225 degrees. And then we have a rotation by 7 times 45 degrees. 7 times 45 degrees. That is 315 degrees. My claim is that all these four, and there are other symmetries by the way. For example, rotation by 90 degrees is also a symmetry. Rotation by 90 degrees is also a symmetry. So you turn, if you turn by 90 degrees, A will go to C, B will go to D, C will go to E, E will go to G, F will go to H, G will go to A, and H will go to B. So entire thing will turn by 90 degrees and you will get the octagon back. So rotation by 90 degrees is also a symmetry, but I'm not going to consider that rotation. By the way, can you tell me how many rotational symmetries does the octagon have? You can give that in the comment section. Alright, so this is these, but I'm picking out these 4, let's change the color. I'm picking out these 4 rotational symmetries because they are quite interesting in their own right. Why is that? Well, let's look at rotation by 135 degree. This one. Rotation by 135 degree. Rotation by 135 degree, if you do it twice, if you do rotation by 135 degree 2 times, you will get rotation by 270 degree, right? You first turn by 135 and then you turn by another 135. Okay, rotation by 135 degree, if you do it 3 times, rotation by 135 degree, if you do it 3 times, what do you get? Well, you rotate by 135 and then 135, that is 270, and then you rotate by another 135, that is 405 degree, right? That is rotation by 405 degree, which is same as rotation by 45 degree, right? Because whenever you are above 360, you are basically rotating once completely and then you are rotating some more. So instead of rotating by 360, you could just not do that, because rotation by 360 will bring you to the same position as you started off with, and then you should just do the remaining, which is simply 45 degree. So 3 times, if you compose it 3 times, so what happens if you compose it 4 times? If you compose rotation by 135 degree 4 times, what would happen? Okay, so then you will have 405 and then you add a 135 more, that is 540 degree, right? I think that's right, 540 degree. But what is 540 degree in, if you just discount the 360 degree rotation? Well, that's simply rotation by 180 degree. 540 degree rotation is 360, so you rotate completely by once, and then you add another 180. So that's 5. So you see what's happening here. You have rotation by 135 degree to start with, and then you do it twice to get 270, do it thrice to get 45, do it 4 times to get 180. So if you do it 5 times, 6 times, 7 times and 8 times, you will get all the rotational symmetries, all of them. So you can check, and this is something I will ask you to check. What happens if you compose it 5 times? It's equivalent to what rotational symmetry? If you compose it 6 times, what do you get? If you compose it 7 times with itself, what will you get? And if you compose it with itself 8 times, what will you get? Turns out that there are 8 rotational symmetries of the octagon, because it's all the multiples of 45 up to 360. So all 8 rotational symmetries will come up just using the rotation by 135, composing it with itself. So these are not only rotational symmetries, they are the generators of all rotational symmetries. That means using one of them, just by composing it with itself, you can generate all of them. You can create all the rotational symmetries. This is very special. This is not true about rotation by 90 degree. You can check. Rotation by 90 degree, but just by composing it with itself, you cannot create rotation by 45 degree. You will only creating the multiples of 90. 45 is not a multiple of 90. So you will not be able to create that. So rotation by 45 degree, rotation by 135 degree, rotation by 5 times 45 degree, that is 225 degree, and rotation by 315 degree. All of these are very special rotational symmetries. They are simply the generators of all rotational symmetries of the octagon. So notice the multiples of 45 that we are using: 1, 3, 5, 7. Do you remember where we saw this? This is exactly here: 1, 3, 5, and 7. So this particular set represents all those special rotational symmetries of an octagon, of a regular octagon, which generate all rotational symmetries of the octagon. Isn't it beautiful how number theory and geometry are connected? See, we are not really trying to memorize a ton of formulas in mathematics. We are here to get inspired by the beauty of it. So if you have some beautiful story of mathematics, maybe from some Math Olympiad program that you are part of, then just let us know. And if you are interested in our programs in mathematics, physics, computer science, ISI-CMI entrance programs or research programs, check the link in the description for more details. All the best and keep on doing good mathematics, alright? Take care, bye.